Okay, welcome to the new participants. I see we're up to 46. So in just in a few more seconds, we will get started. Okay, great. So let's get started. So it's our absolute pleasure to today to host Martha White for a CAIDA invited talk. And so I'll introduce Martha as an associate professor of computing science at the University of Alberta, and so where she is a Canada CFAR AI chair at AMI, which is the Alberta Machine Intelligence Institute. Martha is interested in reinforcement learning and representation learning, among other topics, and more specifically within that in off-policy methods, continual learning, sparse representations in reinforcement learning, and also in a recent a favorite of mine, a paper called Max-Min Q learning, and much more. So today she'll be giving us a talk on rethinking the objective for policy optimization in reinforcement learning. And so I'll be, a number of us will be monitoring both the chat channel and the hands up in the participants box. But if you want, you can also feel free. You should be able to unmute yourself and ask a question directly. And so we'll be fairly serendipitous with that. If at some point there's too many questions, then maybe we'll nudge things along. But in the meantime, welcome, Martha, and look forward to your talk.
Thank you. Well, thanks so much for inviting me. This is going to be fun. So like Michael said, this is going to be about policy optimization and reinforcement learning. And I'd like to try to make it as engaging as possible for everyone. I know not everyone here works on reinforcement learning. So I'd love, if you're not sure what I'm talking about, or if you have any questions, please do unmute yourself and interrupt. Talks are so much more fun when I get to see what you're thinking. And since I don't actually get to see your faces right now, I only get to see a couple faces. It's harder for me to gauge, if you're following or not. So please don't be embarrassed to interrupt. Okay, I'm also going to apologize ahead of time for how low resolution some of the equations and the pictures are in these slides. This was my first attempt at using Google Slides, and apparently Google Slides is just terrible about having high resolution pictures. So maybe that's unimportant to you, but it bothers me, so I felt like I should tell you about it. Okay, so let me start off by just telling you about the reinforcement learning setting, and then I'm sort of going to tell you where this talk is going to go. I'm going to start with a little bit of a history about policy optimization, part of my journey through policy optimization, and how it's led me to what I think is a pretty useful view about policy gradient methods. So first, let me just tell you what reinforcement learning is. Here I have at the bottom, I assume that you know what, I know you know some stuff about machine learning, but maybe that you don't know much about reinforcement learning. So I know there's some of you in the audience who definitely know lots of stuff about reinforcement learning, but I also assume there's some of you who have only maybe barely heard of it. Maybe you've heard of Q learning. So in reinforcement learning, the goal is pretty straightforward. Our goal is to find an optimal policy, and that optimal policy should be one that maximizes the cumulative sum of future rewards. So here in this little standard diagram, the agent's interacting with the environment where it's in some state ST, it gets to take some action AT, transitions to some new state ST plus 1, and receives some reward RT plus 1. So this very general framework encompasses a lot of the settings that we imagine where we have an agent continually interacting with an environment. If you have a robot in the world, its current state S might be something like its location in a room, then its action might be to drive forward. It's going to transition to some new state, let's say a new location in the room, and might receive a reward for that action being a good or a bad action. So getting to a good or a bad state. Now, of course, it has delayed consequences. So the action I take now might give me lots of reward in the future. Let's say I drove towards a part of the room where there's lots of gold and I want to pick up gold. So RL is all about maximizing long-term future rewards, and the agent's goal is going to be to try to learn this optimal policy that gets as much reward as possible. Okay, so then, this talk is all about that question. How do we find the optimal policy? So I'm going to give you maybe a little short history on policy optimization. And here, this is sort of to ground why this is an exciting question, or why some of the things that I want to talk to you about in this talk are exciting. It's going to tell you a little bit about what has been open, And then I'm going to start to show you how we're getting some answers to some of those open questions. Okay, so our goal is to learn an optimal policy. And I'm going to give you a bit more of a crash course in RL later when we get into the technical details. For this very short history, I'm just going to kind of tell you things at a higher level without defining everything too carefully. All right, so anyway, the typical approach in RL has been to learn values. So value-based methods have been very common. And what this means is you might try to learn the values of certain actions. So if you're in some state and you had some function, let's call it an action value function, that told you that one action, action 1, gives you a value of 10, and another action, let's say action 2, gives you a value of 5, well, then it's pretty obvious that you should take action 1. So a common strategy in RL has been to use these methods like Sarsa that learn action values and then just infer what your policy should be. So the dream behind policy gradient methods or direct policy optimization is to say, well, why go to the effort of learning the action values? Maybe we can just directly learn the policy, and maybe that's simpler. Maybe we can actually get to a good solution faster. So the idea with that is we're going to learn a parameterized policy, let's say using some direct gradient descent procedure on an objective. So here you might have some neural network. Let's imagine you parameterize your policy as a neural network. Your policy is pi. It says in this given state st, here's my distribution over the actions I could take. And maybe you've decided you're going to parameterize that distribution as this bimodal Gaussian distribution. So, you have your neural network, it's going to input your state S, it's going to pass through some, your layers, and it's going to output these terms that you need to define your bimodal Gaussian distribution. Okay, and then now you need to do is adjust these policy parameters, theta, that are these network parameters, using some, gradient descent or gradient descent procedure, since we all love gradient descent. And here our G is defined as the cumulative reward obtained by my policy pi theta. And I'll tell you more specifically later what G really is for policy gradient methods. But just imagine you had some objective that was like that said, if we gave me this policy parameter theta, here's how much reward you would receive under that policy. Okay, so that's our goal, is to figure out how to compute this gradient. And this is a pretty straightforward thing you'd want to do, but actually only pretty recently has there been a strategy to compute that gradient. The operations research literature, of course, has been working on these problems for a long time, and they have lots and lots of solutions to our problems. But also many of those works are in the tabular setting. So this nice result from Sutton and others was to give a nice simple form for the gradient of this objective G, and it's called the policy gradient theorem, and it was published in the year 2000. Okay, so this result has been really useful for trying to derive these direct policy gradient methods. Okay, now this was only derived for the on policy setting. Okay, and so the off policy setting, though, is really the more general setting that we care about. Okay, so the off policy setting is for example, very naturally arises in these modern methods that keep buffers of experience or data that they have already seen. Okay, and so you imagine you're an agent wandering around gathering a bunch of data. Maybe longer ago it would be an online setting. You would use a data point and then you would just throw it away. That's not really squeezing as much juice out of the data as is possible. So better is you store some of that data and then you try to reuse it as you're interacting with the world to get as much out of that data as possible. Inherently now this becomes an off policy setting because you're updating with data from an older policy, which is different than your current policy. So the on policy setting is you need to have your data generated according to your current policy, and the off policy setting is you can use data according to any policy. So this off policy setting is really where we want to get to, but unfortunately we didn't actually have an off policy gradient theorem for many years after this. That sort of just remained an open question. So we tried to try to tackle this, but we didn't really answer it fully at all. So in 2012 we introduced an off policy gradient algorithm, and here we did something very simple. We just dropped a part of the gradient that we found inconvenient to try to compute. And then we tried to say something about this update. And really, we were only able to prove very limited results in the tabular case. Actually, that paper, we thought we had a stronger result and then later realized it was a little bit incorrect. So if you go look up this paper, you'll find an errata that says, unfortunately, our results are only for the tabular case. In any case, this was sort of a step forward, and many algorithms actually built on this, what was really easy to use algorithm. Our goal was to find an easy to use algorithm, which is one of the reasons we wanted to drop this part of the gradient, but ultimately it proves to be an unsound update. Okay, nearing the end of this short history, finally, much more recently in 2018, we finally solved this open question and with this paper that we published in NeurIPS. with my PhD student Ehsan Amani and Eric Graves. That's unfortunately the only picture I have of Eric. In any case, we were really excited about this result because first we showed that we actually had a counterexample for our own previous algorithm, which is called off-pack, where we found that it converges to a bad solution even if we started at the optimal solution. So we initialized it at the optimal solution and it would move away to this pretty suboptimal solution. And the key idea for this policy gradient, how to get the true gradient for our objective, was that we just needed to incorporate a different reweighting. So we actually were able to use the same simple gradient. You still could kind of drop this part of the gradient we wanted to drop, but we needed to add an extra reweighting out in front. Very simple, actually. Okay, and adding that reweighting now made it so that we didn't converge to these bad solutions. So you might think, okay, then we're done. You know, we wanted to have direct policy optimization algorithms. We now have policy gradient theorems for the on policy and off policy setting. But unfortunately, the reality seems to be that, you know, generally researchers don't seem to want to use these weightings. So what ends up happening in practice is they use the simpler algorithms that don't have the reweightings, and things seem to kind of work out okay anyway. So, you know, you might say, well, maybe the reason people don't use these reweightings is that paper was published in 2018, but actually this problem exists in on-policy learning too, where that result has been around for many years. And there's even these nice papers by Phil Thomas that show that there's bias in many on-policy policy gradient methods because they also don't want to use the weighting you're supposed to use for the on-policy setting. I particularly like this provocative name. Is the policy gradient a gradient, question mark? And they show that it is in fact not the gradient, that the current ones that are used are not actually the gradient of any function. So what's happening here? You know, the simple incorrect update is widely used in the off policy setting and really in the on policy setting. And so why would we use this incorrect policy gradient? Why not use the correct ones that we actually have? Well, it seems like the answer is the standard answer. It's simpler to use the incorrect one. So naturally people are going to gravitate towards something that's simpler. The reweighting out in front is actually not that complicated, but it can be a little finicky. So it can get very small, which seems like it could cause some variance issues. So as soon as there's any kinds of optimization issues, the natural thing is to say, okay, never mind. I'm just going to go to the thing that everyone else uses that seems to work okay. I have some other hypotheses about why we still use them. One of them is that maybe these incorrect algorithms are actually just working well, and our theory is not covering why they are working well. So we have limited theory. These algorithms aren't incorrect. Actually, rather, they're good algorithms, just our theory doesn't characterize that they are good. Mark actually recently gave a talk at U of A about these interesting conditions where if you have over-parameterized networks, then you can get exact zero gradients for every individual point. So I can imagine with our over-parameterized networks, maybe weightings are not that important either. So there's all these reasons why maybe this incorrect update is still being used, and you know the correct policy gradients are not being used. But whatever the reason is, the incorrect update, it does define many policy gradient methods that are currently used out there. They are not actually using the true policy gradient. So we have a natural question then. If these methods are not gradient methods, then what are they? How can we actually characterize them? So that's sort of my goal. I wanted to step back and say, well, is there some other way we can interpret these methods and then maybe understand why it is that they are performing well or how we can modify them to make them better? Okay, so that's going to be the goals for my talk. That sort of sets up the sort of history about why policy gradient is actually not an easy problem and some of the progress you've made, but how there still sort of seems to be this gap between what's used in practice and what our theory says we should be using, specifically about these weightings. So I'm going to start off with this topic about approximate policy iteration, and then work my way back towards that motivation of how is this all connected to policy gradient methods. So first I'm going to tell you about approximate policy iteration, which is a strategy that combines value estimation and greedification to find optimal policies. I will tell you what it is. And then in this, I'm going to motivate for you why, on top of what's usually just value-based methods, we're going to learn explicit parameterized policies in this API framework. And then I'm going to tell you about our recent work where we were actually investigating these parameterized policies inside API. So all these first three steps are really just going to be to show you a more general framework about how we can design algorithms to learn parameterized policies. And then I'm going to bring it back to how this relates to policy gradient methods, and that you can actually think of many policy gradient methods, in fact, as these methods that I'll tell you about, these API methods, and then what the implications of this are. So they'll almost seem like a little bit of a disconnect for a while from this first short history to what we eventually get to. But really for me, the more general view, I'm going to be pitching that a good general view for policy gradient methods might be to think of them as API and explore that direction. Okay. And as we go through, I'll try to have sort of some natural breaks so you can ask questions if you have any questions. So as a quick run through and background, our problem is formulated as a Markov decision process in reinforcement learning. What that means is we're going to assume we have some set of states and actions. These states can either be continuous sets, so you can have ranges of values for states between 0 and 1, or you can have finite states. And we're going to assume that we have these Markov dynamics, which means that whenever we're in a state, when we're in a state and we take an action, we're going to have some distribution over next states and rewards. And it's Markov in that you don't need to know the state before this current state. So if you're in state S0, you transition to S1, and then you transition to S2, the distribution over S2 would not be impacted by knowing what the value of S0 was. It's sufficient to know what S1 was. Okay, and we also have a discount parameter gamma that tells us what the horizon is that we care for our return. So I'll tell you what the return is, and you'll see naturally what this discount parameter does. Okay, so one of the quantities we're often going to care about is the values of our policies. So the action values are defined this way. If we imagine we have a fixed policy, so imagine I just hand you a policy, let's say whatever you're currently doing. It may not be the optimal policy, it's just some way of behaving. And now we want to know what is the value of this policy from some state and action. So this means if I was in a state and I took an action, what would be the expected return? How much reward would I get if I were to continue following the policy from here on out? So that's defined here. What this is saying is that Q pi, which is our action value for policy pi, saying if I start in state at time t, if I'm in state S and I take action A, then this is the cumulative reward into the future I will receive in expectation. So I have my immediate reward plus gamma times my next reward plus gamma squared times my next reward. So this gamma is discounting how much I care about rewards in the future. In one extreme, if gamma is 0, then all these terms in the future are zeroed out, and I only care about my immediate reward. And if gamma is very close to 1, then I care a lot about future rewards. Okay, so it sort of gives you a natural way to care about your horizon. So now if we were to try to think about estimating these action values, many methods do try to estimate action values. This seems like a tough thing to do. You would have to go get samples of these really long returns into the future. But sort of fortunately, because of the nice structure in our problem, we're going to be able to break this up into this recursive form, where if you notice this inner term here, if we just pull a gamma out in front, then we have RT plus 2 plus gamma times RT plus 3, and so on. And you can see that this term is, again, just the value, but now starting in the next state. So starting from ST plus 1, given that I took AT plus 1. So we can replace this whole term here with just this term here. And now we're going to get all the algorithms that we know and love in reinforcement learning. Particularly Sarsa is an algorithm that's going to take advantage of this. So the idea here now is if we want to update our value estimates, if we actually want to estimate these action values, we're going to have to learn some parameterized action values. Let's call that QW. That's trying to approximate Q pi. So the W means the weights that are, for example, the weights in the neural network that we're using to estimate Q. Okay, now if we wanted to go estimate Q towards expected returns, we don't want to have to wait for the entire return. So we're going to use this trick where we're going to take our estimate of the return from the next state under our current estimate, and we're going to pretend like this target here is an actual estimate of the return. So it's going to be immediate reward plus gamma times what I currently think is my actual return from the next, expected return from the next state. So if you look at this update, it looks just like a regular regression update. Delta tells you what error you had. So you have target minus your prediction about what that value should have been for the target. And then you just take the gradient of your function that's giving you your prediction. So you can sort of think of Sarsa like doing regression. That's saying I'm trying to get my function to predict well what the true expected value is for given S and A. And the only real difference is that instead of using the actual targets that we should be using, returns, we're going to be using these sort of biased estimates of our returns. Now there's good reasons to believe that this works well. Sometimes it's a good idea, sometimes it's a bad idea. It might actually be problematic that we use this bootstrapping target instead of true returns, but that's for another talk. So we're going to assume that Sarsa is a great choice to use, and we're going to go forth with it as our strategy for estimating action values. Okay, so now that we have our action values and we have Sarsa, we're finally going to get to where this idea of approximate policy iteration comes in. Okay, so remember, our goal is not to estimate the action values for a specific policy. Our goal is to try to find the optimal policy. So we have this nice result, the policy improvement theorem, that tells us a simple strategy for getting the optimal policy. So let's imagine you do have some strategy to get Q pi for the current policy. Let's say you have Sarsa. The policy improvement theorem says that if we were to act greedily with respect to Q pi, that's just going to produce a new policy for us that's better until we get to an optimal policy. Okay, so here we're going to define this pi prime that's going to take maximal actions according to the current Q pi. So it's going to say whatever action my current Q pi thinks is good, I'm going to act according to that. Whereas this previous policy wasn't necessarily taking those maximal actions. And this theorem says that this pi prime is going to be better than the previous pi. Now that's sort of intuitive. What it's saying is that in each state, if I'm going to get to pick an action, if I pick the action that is the best, then of course that policy should be better than a policy pi that isn't necessarily picking the action that is the best according to Q pi. There's more nuance to it than that, but it's sort of an intuitive result. So then we get a very simple idea from this. We're just going to alternate between estimating Q pi, then we're going to greedify. So we're going to go pick the greedy policy with respect to Q pi, then we're going to estimate Q pi prime, and then we're going to keep doing that until we reach an optimal policy. So that's where we finally get to policy iteration and most of the end of this background. So the idea behind many algorithms actually, particularly these value-based algorithms, is to do something like this policy iteration approach. So here I'm just going to use V for value instead of Q for action value, but V is the word value. So we imagine we start at some policy pi, then we go and get the true action values for that policy pi. So we get to this line that tells us the true V pi or Q pi for our policy. Then we go get the perfectly greedy policy according to that new action value. We keep iterating this process, and we're actually guaranteed to eventually get to our optimal pi star over here. That was our goal. Okay. So we can't actually use policy iteration. Rather, what we're going to use is approximate policy iteration, and then we're going to have interesting questions about how we're going to do each of the steps in policy iteration. So let me just tell you first why we can't do policy iteration, or why we also wouldn't necessarily want to do full policy iteration. So the main problem with policy iteration is that it requires you to go get the true Q pi and then to go perfectly greedify and to alternate with these pretty expensive steps. So for the first case, it's pretty sample efficient. It could take lots of samples to estimate our Q pi, but we don't really need to estimate Q pi that accurately to act well. So you can imagine you have a really bad policy, and then you spend many, many steps trying to figure out what Q pi is, when all you really needed to know is that action 2 and 3 are really terrible and action 1 is better. And you didn't need to get very precise estimates of Q pi. So it's sort of a wasteful thing to do, to try to go spend a lot of time to go get Q pi, both in terms of samples and in terms of computation. So let's not do that. That seems like an unnecessary thing to do. So the first step in policy iteration that most algorithms do is to approximate the value update. So here now when we start some policy pi, we're going to do some value updates, but we're not going to update all the way until we get to Q pi. We're just going to stop a bit early and say good enough, and then we're going to go greedify. And then again, we're going to do this not fully, and we're still going to be able to, in some cases, show that this is going to converge to the optimal policy. So now a lot of approximate policy iteration methods, though, do still do this full greedification step here. They'll do approximate values, but then they'll go get the maximal action. So if you've ever used Q-learning or Sarsa, really implicitly, they're always going and getting the greedy policy because they're taking the action values and then they're saying, go find for me the max A, which is immediately just telling you what the greedy policy is. So in general, this is a fine thing to do, and it makes sense why in API, most methods are doing something like this picture. But this story gets a little bit more complicated with continuous actions. So in continuous actions, that greedy step is going to be harder. So the second issue with full policy iteration is that computing the greedy policy exactly can be very expensive. And mainly this is for continuous actions that it can be very expensive. Let me explain why that's the case. So let's imagine you were trying to do this step where you're going to go find the maximal action. So you're going to imagine someone hands you some estimate Q, and it doesn't matter if it's a good Q or not. Your only goal in the greedification step is to act greedily with respect to that Q. So you want to go compute this function pi of s that returns the argmax action. So let's do a regular setting. We're going to imagine QSA is a neural network, and we could try this very straightforward strategy that has been used. So you could use gradient ascent to find this maximal action. So what that means is you would start at some action A, and then you could actually go find the gradient of Q in terms of A. So not in terms of its weights, just to be clear here, you would actually try to perturb that input A and then start to rise on this surface until you reached an A that made this value as large as possible. Okay, so that's actually a fine idea. Like I said, it's been used in practice, but it is a little bit problematic in that it can be very expensive to solve that optimization problem. And as we'd imagine, QSA is usually non-convex in A, so we're not really going to be actually getting to that maximal action. I'm just going to point out here that we have also worked on this problem about how do you find the maximal action for Q learning. It's a paper that's in archive right now, but it's currently in revision because of the things that we realized that are in this talk. So we worked on this first paper on archive, then we realized some things and had to work on these other ideas first, and then we're going to come back and revise that paper. So you'll find that paper in a bit of an interim state, but you might still find it interesting to summarize some of the methods that do this. Okay, so what can we do instead? Well, we're going to try to do an approximate greedification instead. Okay, and so for that, we're going to learn a policy that's going to output these maximal actions. I think I have to speed up here a little bit. Okay, so you can imagine a very simple setting where you could use regression, where for each state, some oracle tells you what the maximal action is. If you had such a beautiful data set, maybe you could go and directly learn such a function. That's sort of the idea. That's what we're going to try to mimic. We're going to try to figure out a way to learn a function, a policy that's going to return for us these maximal actions or some distribution over actions. I'm going to continue. I do want to mention one other thing about why we care so much about maintaining an explicit policy. So you might say, well, whatever, I'm just going to solve that max action problem on the fly. I'm really good at optimization. At UBC, for example, you guys are really good at optimization. But really what we want from our agents is to have reactive policies. So I might actually be okay with my agent using a very slow learning strategy in the back where it carefully figures out what the maximal actions are and then sort of distills that out into a policy. But when I want to deploy it in the world, or I want it to start actually interacting with the world, I want it to be able to take actions quickly. So I don't want a robot sitting in the middle of the room and then it's computing for a minute while it decides whether it's going to drive forward or not. I'd like it to be able to quickly react and then maybe learn slowly in the background. So hopefully we can distill out this simple policy rather than trying to solve these hard optimization problems each time we need to make decisions. That's sort of the key motivation. Okay, so we finally get to approximate policy iteration. Okay, and here the idea is exactly this. Now we don't have to do either of these things to full completion. We're going to do approximate value updates. We're going to stop early because we don't need to get the full Q pi. Then we're going to do some greedification steps, but we're not going to get all the way to this greedy line because, again, that would be computationally intensive and maybe unnecessary. And we'll sort of do this instead and hope that we can get to a good solution. Okay, so what this is going to look like in practice, just to sort of ground this out a little bit in something that looks like pseudocode, it's very simple. Again, we might imagine we store a buffer of experience. We're going to sample some transition from that buffer. And then we're going to update our action values. We're going to do that one step, let's say a value function approximation. So you might do Sarsa update on that transition. And then maybe you'll do one step of approximate greedification. So you're going to go and use some objective that tells you how am I going to do that one step of greedification. And now for us, the question is, what should this G be? How are we going to get it to, travel down this arrow towards a more greedy policy? Okay, good. So this is a chance for anyone to ask any questions about, the motivation, how this works. Just to give a brief summary of what I just told you about. Policy iteration is this nice general framework. API is what we actually use to try to practically implement this idea. It has rarely been the case that API has actually been used with approximate greedification. Almost always it's been used with approximate value updates and exact greedification. So there's actually going to be some interesting open questions about approximate greedification. And we care a lot about the approximate greedification step because we want to do continuous actions. So that's generally summarizing what I wanted to get across in this first bit. I'll pause here for 30 seconds in case there's any questions. Oh, could I discuss briefly when bootstrapping methods fail? Let's see. That could take a little bit of time, but I can tell you they succeed in the tabular setting. They succeed under certain linear function approximation settings if you have the right weightings. They fail often if we're not careful. So I can maybe I'll take some time at the end if you want to ask that question. In theory, they can fail often. In practice, also doesn't seem like they fail that often. Okay, I guess I'll keep going. It's always a little disconcerting to me when there aren't more questions because, then maybe this went a little too quick. Or it was really slow when you got it very well.
I'll just
That
say
would be
it's great so far. So there you
okay.
go for feedback.
Okay,
So you're not
great.
working in a void.
Good. Thank you. Thank you. It's helpful to know. Okay, so that's the summary so far. And now this is sort of getting us closer to, you can already see that we must be getting a little closer to policy gradient methods because this approximate gradification step is going to include some gradient with respect to our policy parameters. And then we're going to start seeing how things actually look a lot like policy gradient methods. But let's first anyway ask this question that I want to answer this question I wanted to answer, which is how are we going to do this approximate gradification? So like I said, this has been surprisingly understudied. So there are actually methods out there that of course do approximate gradification, often because they needed to within their own algorithm, they needed to propose something. But what has been less studied is how important this choice is in sort of a systematic way. So recognizing that there is this important approximate gradification step and then trying to systematically go through, well, what are our options and what are the pros and cons to this options? So algorithms exist, but mostly in isolation. And I think mainly this has been sort of understudied because it hasn't risen very much. In the discrete action case, which is what is by far the most common case in RL, even though I know lots of people use policy gradient for continuous actions, but still, by far the most common setting is discrete actions. And there it just doesn't come up the same way. It's so much easier to get the max action. There's not the same need to do approximate gradification. Okay, so one of our contributions is to identify what we think are 4 interesting choices for approximate gradification and then really try to in-depth understand what their pros and cons are. So let me just give you a brief overview of what those choices are and sort of what our conclusions are. I won't be able to go through all the things that we did there. And then finally, I'll conclude by connecting back to how one of those choices actually ends up corresponding to a large class of policy gradient methods. And we otherwise categorize other policy gradient methods as the other choices. Okay, so first thing we're going to have to do, so I've already told you we're going to do approximate gradification, but we're not actually going to do the exact gradification I told you. Sorry, this should be an argmax here. What we're really going to do is this more general thing called soft gradification. And for that, one of the reasons we want to do that is we don't actually want to extract usually deterministic policies. We really like to have stochastic policies. They're going to let us explore a little bit more, and they also just have some nice robustness properties. So instead, we might want to do this kind of thing. So here, what we're going to try to do is extract this policy that we're going to call the soft greedy policy that corresponds to this Boltzmann distribution over the action values. I'll show you on the next slide why it is that this helps you learn policies that concentrate probability around high valued actions. But anyway, this is really, you can think of it like a greedification because it's going to return for you a policy that has put most of its probability around values that are high. Okay, so we're going to consider mostly option 2, also just because it's more general than option 1. As you allow this temperature parameter tau to get smaller, then you're really just approaching the same typical argmax. So let me show you a diagram of that. So this is one of the experiments that we looked at. We just took a very simple setting with 1 state or 0 states, whatever you'd like to call it, a bandit setting, where we had these action values that were continuous, and this is what the values are across all the actions. And the actions go from -1 to +1. Okay, and so then if we were looking at these action values, we can ask, well, what would the Boltzmann policy look like? So you can kind of get some intuition about what that looks like. As the temperature parameter, for larger temperature parameters, it's starting to get flatter. So even with tau is equal to 1, it's a little flatter or smoother than these action values here. If tau actually got bigger, you would start to see this much smoother distribution as well. And then as tau gets smaller, it's going to start peaking the Boltzmann distribution around these large valued actions. So here already it's starting to peak much more around this maximal action here and less around this action. Just to be clear, the argmax action is this one. It's the one with the highest value. It's just that locally in this region, this one also has reasonable value compared to the other actions. But this is the true maximal action right here. Okay, so as tau gets smaller, you can kind of see how this looks like. And as tau gets very small, all the way to 0, then really we just have this Dirac delta around the maximal action. So this tau gives us a way to sort of say how stochastic we want our policy to be. If it's 0, we're saying go get that deterministic policy, and otherwise we're adding a little bit of stochasticity. Okay, so this is now going to be our goal then. Our goal is going to be to find this parameterized policy pi theta that's going to approximate this Boltzmann distribution And now we can again ask that. So now we've decided what we believe our greedification policy should be. We can acknowledge that we can't perfectly obtain this. This is going to be generally difficult to sample from, so we don't want to use this form explicitly. And rather, we'd like to distill it into some simple, let's say, Gaussian policy. So we're going to do the most natural thing, also the thing that's most commonly used in practice, which is, and we would like to try to characterize what people are actually using. So we're going to choose this a KL divergence between our pi theta and this exact greedification policy, this Boltzmann policy here. And our goal is going to be, to try to investigate the properties of these two different objectives. Now, the KL divergence is not symmetric, so it does give us these two options. We have the forward KL and the reverse KL, where if you put pi first or pi theta first, it results in two different looking objectives. So let me just show you what those objectives look like. This slide has a lot of math, so let me just go through a little bit more slowly. If you forget what the KL looks like, it looks like this term here. So the first policy, pi 1, is telling you how you're sampling your actions, and then you're looking at this ratio between P1 and P2 across our actions. So down here you can see why it impacts things that you have one first versus the other. Okay, so when we look at the forward KL, because the Boltzmann distribution is first, it's the thing that we're sampling our actions according to. So it's our weighting inside this integral, and then we're sort of saying, look at the likelihood of the actions that are distributed according to this Boltzmann. And the reverse KL is weighting this integral by the policy pi theta, and then additionally has this entropy term on our pi theta. So if you were to sort of try to interpret what these two objectives look like, this second objective is saying, here, if you look at this integral, what it says is take, for all the actions that have high value, in order to make this number small, do I have this backwards? Yeah, okay, sorry. In order to make this number big, which means the negative of it is small, I want to put as much probability mass on high valued actions. So it's going to try to concentrate as much as possible on actions where Q is very big, which is sort of what we want. We want to do that greedification. But now we don't want it to collapse fully, so this entropy term here is saying, but find the maximal entropy policy that also satisfies that property. So it's going to keep some stochasticity there. Whereas the forward KL is instead saying, sort of make the likelihood of the actions that are high probability under my Boltzmann distribution, also make those high probability on my parameterized distribution. So slightly different. So regardless of exactly what the math looks like, we can kind of reason about what are the differences between these two choices, at a high level. Why might we expect there to actually be different properties? Okay, so the first sort of main difference is this idea of mean-seeking versus mode-seeking behavior. So in that, like I pointed out, in that forward KL, it sort of needs to try to match that full distribution. It's going to incur lots of penalty if pi is big and it tries to make the probabilities for those actions small. Whereas actually the reverse KL won't necessarily incur penalty for that. So there could be high probability values under pi for an action. And if pi theta has 0 probability in that region, it doesn't actually get included in this integral. So that means that pi theta can actually choose to match one mode as much as possible and completely ignore another mode without incurring too much penalty, whereas that would be a lot of penalty for the FKL. And now then, so you could argue that mode seeking, mean seeking, and one is better than the other. I kind of like the idea of mode seeking, but I've heard good arguments for mean seeking as well. So that just is a property, whether it's a good or a bad thing. The next two properties are clearly good and bad. And that's why they have smiley faces or frowny faces. So the one bad thing about the forward KL is that it can be hard to sample, because in order to actually get gradients according to this, in order to compute our gradients, we need to sample according to this BQ to get actions sampled according to that Boltzmann distribution, and that can be expensive. So it's sort of hard to optimize this objective. Whereas for the RKL, we just have to sample from our own policy, and presumably we've picked a reasonably simple policy, like a Gaussian policy, that's easy to sample. And then on the flip side, even though it's harder to optimize the FQL and just strictly in a computational sense, the actual optimization itself might be easier. So there's at least some nice convexity properties for the forward KL, whereas the reverse KL is going to be non-convex in general. So this is, sort of using these ideas about how FKL and RKL, the forward KL and the reverse KL, just their general properties. We kind of try to design some experiments to elucidate how much do these things happen in our actual RL setting, where we might imagine it's a little bit different. Okay, so I'll just point out one kind of interesting thing we noticed, that we did actually find some mean seeking versus mode seeking behavior. So going back to that simple bimodal example I showed you, when we took, so we had this blue distribution, that's that Boltzmann distribution with a tau here of 0.4. And when we actually went and optimized, we got the true optimal for the FKL and RKL, regardless of how bad their optimization surface is. We went and got those true optimal values. And the FKL really did have this mean-seeking behavior, and the RKL, this green line, is concentrated on this single mode. So that was sort of neat that, you know, that's what we should expect to happen, but it's always, experiments never match what we expect. So it's kind of interesting when they do match what we expect. At the same time, this mean-seeking versus mode-seeking behavior very rarely happened. We had to pick tau very specifically, and otherwise, actually, FKL and RKL performed pretty similarly in terms of that behavior. So in fact, I have a slide of that right here. I'm going to quickly jump to it. Here, when we looked at some of the other temperatures tau, really they ended up concentrating on the distribution very similarly. Okay, I want to leave you guys enough time to answer questions. So I'm going to probably, can I put back? I'm going to probably skip this slide and what's happening here exactly. But I just want to point out that we looked at, when I said we looked at 4 variants, what I really mean is we looked at FKL and RKL with tau is equal to 0 or tau greater than 0. Because actually with tau not equal to 0, we no longer have entropy regularization, and things just really become different when you don't have entropy regularization. You end up with these hard objectives that look quite different than their soft versions. This one looks something like trying to maximize the likelihood of maximal actions, just those maximal actions. And as we're going to see, this hard RKL looks just like the actor, critic, or policy gradient updates. So I'm gonna continue though. I'll mention a couple things about this result because it's the only other experimental result I'm going to include. So like I said, we had sort of hypotheses about what we expected from these methods, and they were largely verified by our experiments, but some of them, like I said, were maybe less emphasized than I thought they would be, like the fact that mean-seeking, mode-seeking behavior really didn't seem to arise often. It only happened very infrequently. That's happening here, and everywhere else they sort of behave similarly. So once the temperature parameter became large enough, these two lines are just overlapping and they behave similarly. Their optimization surfaces, though, clearly had different patterns. So this first row shows the forward KL, the second row shows the reverse KL, and the reverse KL clearly has these two regions where there's a local minima here, and then there's, you know, the optimal solution over here. And the forward KL didn't have this. All values pointed towards this global solution. I'm not sure if there's anything else that's particularly important for this one, so I'll continue, and then later if anyone has questions, yeah, you can ask me.
Just a quick question on symmetric KL. So that would be, I guess, the landscape for that would be some kind of blend of those that you're showing, I guess.
Yeah, that's a great question. Someone has brought up the symmetric KL before too. I would imagine it would be some blend. Like I would imagine it should maintain some of this non-convexity that we see here, but actually I'm not sure. So we should really add an additional row here where we see what that surface looks like. Yeah, maybe we would see it much less pronounced because here it's such a strongly pronounced here. Maybe we would see just something light here. Again, I'm not sure. Okay, so our overall conclusions from these, from this work actually, and overall. So I have a comment here at the bottom that this paper is actually not released yet, but if you wanted to see it, you could always email us or otherwise wait a couple months and it'll be up on archive soon. It's under review, so we didn't want to release it. But I didn't say anything about the theory, but we actually have some theoretical differences between RKL and FKL as well. And actually, our theory says that RKL has better policy improvement guarantees than FKL. And in fact, we have a counterexample where FKL might if you do approximate greedification, you might actually fail to improve the policy, which is a bit disappointing. We do have a limited result where FKL can guarantee policy improvement as long as your temperature is small enough. But it is a pretty limited result. So the theory sort of suggests that in terms of policy improvement, the RKL is a good choice. Our experiments, though, kind of show that the FKL is pretty promising, both in terms of, you know, the fact that the optimization surface looks nicer, but also it seemed to have this benefit that it learned a little bit more slowly. It seemed to concentrate a little less quickly, and this contrasted the RKL, which seemed to concentrate a little too quickly sometimes. It learned faster, but then it kind of plateaued at this worst point. So there does seem to be something promising about maybe learning a bit more slowly and continuing to improve under the FKL. But really, we do need to do more experiments for this. Otherwise, our overall conclusions were, for discrete actions, there was rarely too much difference between them. It was more different in continuous actions, and the choice of tau was very important. It was definitely a dominant factor. Okay, in the last, I think I have 5 minutes so I can leave enough time for discussion and questions and stuff. I'm going to finally come to how is, API connected to policy gradient methods. Okay, so all of this was, all of that stuff up front was just hopefully useful anyway. You might want to know, how can I do approximate policy iteration? What are my options if I wanted to learn parameterized policies in reinforcement learning? And you could use API and all these different objectives to do so as for greedification. But I think it's also helpful to sort of come back to policy gradient methods and sort of see how connected are the two, and can we actually categorize some of our policy gradient methods as API. So in order to actually show you that that's possible, I kind of need to tell you just a little bit more about how do we usually formulate policy gradient methods. Only really one slide for this. So I alluded to this objective in the beginning for what the policy gradient objective is, but the typical policy gradient objective is this one. So usually we're talking about the episodic setting, which means the agent sees essentially little snippets of tasks where it gets to start in some set of start states, and then it completes an episode. The most natural example is like a grid world, where it starts in some part of a world and it has to navigate to some goal, and then it gets teleported back to some start state. So in such an environment, your goal is to try to get across the set of possible start states. You want to get the agent that has the highest value. So this corresponds to the value of the agent. So we're going to go maximize over pi, so that on average across start states, the value from those start states, if I were to follow policy pi, is high. That's what this is saying. Okay, so I had mentioned that the policy gradient theorem is this beautifully elegant thing, because actually if you look at this, computing the gradient of this thing looks pretty onerous. You have to compute the gradient of q pi, and q itself is implicitly, pi influences in some implicit way. So you would imagine there should be some gradient of q pi in our policy gradient. But this theorem nicely shows us that we don't actually need to have this a gradient of q pi. Instead, our gradient looks like the following thing. So we just need the gradient of pi theta, which should be easy for us to compute. We have parameterized it as a neural network or something. And then we just have weightings according to q pi theta. And we have this additional discounted state visitation. So our weighting over states depends on pi theta. Our action values depend on pi theta, but we only have to compute the gradient of this. So we can hope to estimate these and hope to sample proportionally to however our pi theta visits our states. Okay, I had already told you that most implementations don't actually use this gradient. For example, many actor-critic methods just drop the weighting that's associated with state visitation. So they'll compute that inner gradient, but they won't necessarily pay attention to if they've actually weighted according to discounted state visitation. And this is really true for almost all algorithms that you would use out there. At least I believe so. So back to this question, if you're not using policy gradient, then what are they doing? Well, one answer that we're providing is that actor-critic methods might actually be doing something like API with a hard RKL. And I'll just show you why that's true. So just to write out what an actor-critic approach might look like, again, you'd keep a buffer of transitions. You're going to sample one of the transitions or mini batch. You might update your action values with Sarsa, and then you're going to update your policy with an estimate of this policy gradient. Okay, and the estimate of the policy gradient would look something like this thing here. So this looks similar to this term here. But if we actually look at what their expected gradient, if we compare their expected gradients, I know there's a log here, but you can kind of ignore that log. The expected gradient for this thing is equal to this. So what this is saying is, if I had some implicit distribution over my states that's imposed by my replay buffer, I look at my density across states that would be induced by the fact that I'm sampling states according to my replay buffer. Let's call that D replay. This is what I actually use, and this is what I should be using if I were to use the true policy gradient. So this inner term looks sort of similar. The difference is that we use an estimate Q instead of Q pi theta. That's already a little bit problematic. But anyway, at least we're trying really hard to go from Q to Q pi theta. But this part is very different. So the replay buffer could have a much different distribution than the D pi theta. So rather though, if we look at, for example, what the gradient looks like for the RKL, I'm just gonna highlight these things. If tau is equal to 0, we can ignore this entropy term, and then we just look at these two terms. So if we look at the gradient of the RKL, that gradient is exactly the same as this gradient in actor-critic. And then we just have to explain, what about this weighting? So I didn't tell you anything about weightings in the RKL. I'll just tell you briefly that, of course, we had to define weightings. I just didn't want to tell you about it until we needed it. So whenever we do function approximation, we always do have to decide how am I going to trade off my function approximation resources across states. So when we optimized our RKL, we also had to pick some distribution D of S. Now our D of S can be whatever we choose our D of S to be, because it's not starting from the policy gradient objective. It's just saying, how do I want to allocate function approximation resources? Which states are most important to me to get right. So this just becomes a generic weighting. If we chose to set it to D replay, for example, then really we're exactly getting a standard Actor-Critic implementation, and we can think of Actor-Critic as doing API with the RKL. Otherwise, if we could even choose to set D to this D pi theta, Q to Q pi, and then we're really getting a true policy gradient. So it's sort of a more general way to look at this larger class of policy gradient methods. Okay, this is my second last slide, so I'll just sort of summarize what I'm trying to tell you, why this is actually a useful thing to have. So the first one really is it just provides a different way, or a way to understand many policy gradient methods that are not obviously using a policy gradient. So if, like I said, if they're not using a policy gradient, what are they doing? Well, maybe they're doing something like API. And then that categorization, unifications can be useful, but they aren't always useful. But in this case, I think it's useful because it sort of identifies three important choices that we would make in our policy gradient methods. One is this weighting, and then of course the other one is how do you do that greedification, but a little bit more deeply. In that greedification, should we use a forward or reverse KL, and should we use entropy regularization or not? And actually a lot of different policy gradient methods are sort of implicitly making this choice and can be put into any of these categories. So I think we found policy gradient methods that fit all the categories except for maybe the forward KL without entropy regularization. I don't think we ever found one that did that. The other thing I think is useful about this view is it lets us look at a broader class of algorithms for policy optimization. So really we can think of other greedification operators, and it lets us look more carefully about what is the choice of FKL, for example. That was looked to us like a promising direction and could now maybe be more studied specifically in isolation outside of other implementation choices in these large policy gradient methods. Okay, and then the final thing is there's actually some nice theory for API that looks like it's a little different than the theory for policy gradient methods, and you could hope that we might actually then use this view to say, well, can we go borrow theory from API and say something about the soundness of these methods that seem to work reasonably well in practice, but are clearly not using an unbiased gradient. Okay, so the key takeaways from all of this is hopefully maybe just the most basically that learning parameterized policies is useful. So continuous actions or discrete actions, it's better to start expanding our set of algorithms and our understanding of algorithms that are learning parameterized policies. Our current policy gradient theory is maybe not fully characterizing the algorithms that we actually use in practice, and maybe API can provide a more general approach to both develop and understand our policy optimization algorithms. And so for me, I'll just leave you with three questions that I think are really important, open next questions. The first one's sort of obvious. I want to have better understanding of approximate greedification approaches. That's just a really fun algorithmic question. There's so many options we can do there. We have just started scratching the surface of that. I'm really excited about more general convergence theory for API. Doina's group has a neat paper about both doing approximate greedification and approximate value updating, is one of the maybe most promising papers, but it doesn't perfectly apply here. So I see a pretty big open question here. And then finally, for me, I'm sort of obsessed with weightings, but I want to know what weightings besides this d pi provide good solutions. So the answer I definitely know is not going to be any weighting, because we already have a counterexample that would apply to this API setting as well, that says if you use the weighting that we use in our counterexample, you would definitely not converge to a good solution. So it's not going to be the space of all weightings. I doubt it's going to be just d pi. There's probably some in-between space of weightings that are easier to use but provide good solutions. All right, thank you.
Cool, great, thanks a lot. I really enjoyed that. So I'll open the floor to questions, and while folks are thinking of their question, I'll start off with a question of my own. And so I guess the the difference between that involves the inclusion of that distribution or not, it depends. Depends mostly on the episodic structure, and so I guess I just practically from some of the experiments with their own group, I guess that would be a function of how often it terminates early and that kind of thing, just because they're often, well, yeah, I guess it depends on the terminal length of the episodes, and I guess it depends on the behavior of what behavior is actually being encouraged as well. Like, is it cyclic in structure, or I'm wondering if you've encountered any of those things, and in thinking of your counter examples, what do those look like, and just issues on how badly that distribution can impact the result.
Right. I mean, I guess what I would say is that for a lot of our methods aren't so off policy, in the sense that this weighting that we need to have is this discounted weighting into the future, starting from some states under your policy pie. So even as your policy is changing over the last few episodes, it probably hasn't changed so much, so that the data you saw under your policy the last couple episodes ago is maybe not so different from your state visitation under your current policy. So for our largely kind of sticking closer to the on-policy setting, I can imagine that we're not running into such big problems. If we're looking more at like an offline batch setting, where you like some other completely different policy generated data, or like you're really randomizing your policy a lot, I can imagine it rising a lot more. There is an additional thing that there's technically a gamma in the weighting, so you do have to sort of discount states further along in the episode. And so if your gamma is really close to 1 and your episodes are not that long, that also doesn't have a big impact. But again, if your gamma is smaller, now maybe it does have a bigger impact.
Yep. Okay. No, great. That makes a lot of sense. Let's see. Yeah, there's a question in the chat. If you can, I'll just let you read that.
Okay, so find initial policy for Q-learning. When we use linear function to approximate the Q function, it looks not easy to find an initial policy. Okay, so maybe what you're saying is that when we have, if we have our action values and we're trying to extract a policy from those action values, it'll be very incorrect. Or let me see if I can understand.
Yeah, I know someone is working on the experiment. They say that if we use a linear function to approximate a Q function, that probably leads to the divergence of their algorithm.
I see what you're saying. Okay, so maybe what you're saying is that, sure, we can talk about API by building on, like, if only we could do greedification, it would be awesome. But then it's forgetting that the action values themselves might have problems in how they're updated. So we're greedifying a diverging action value, for example.
Yeah, exactly.
Is that what you're saying?
Yeah, is that a possible way to find a good initial policies, or it is an open problem?
Yeah, okay, so that's a great question. I think that the second question about how do we get convergent action value algorithms is a super fun question, also something I'm working a bunch on. The reason Q-learning might diverge with function approximation, I think, is what you're saying. So when you have if you had a policy that, say, has a strange distribution, like the stationary distribution it induces is very bad for Q-learning, then Q-learning might diverge, I think is what you're talking about.
Yeah,
maybe even more, sorry, go ahead.
Yeah, you are right. Yeah.
Right. Yeah, I think that's a problem we absolutely need to solve. I mean, maybe you've heard of these gradient Q-learning methods. So there's, TD and Q-learning both suffer from a similar problem in that they're both based on these, I'll just talk about TD, I guess. TD is based on an iterative system solving underlying update. It's not actually a gradient update. Rather, you should think of it like a stochastic iterative system solver. And that iterative system solver, the matrix underneath it, is not positive semi-definite unless you have a stationary distribution that's carefully chosen. So then instead you have this expansion, and TD spirals out of control because now you're constantly doing this iterative update that's an expansion. So Q-learning sort of similarly suffers from the fact that it's not a gradient update and it could be doing expansions. So the solution that people have been taking is, one is to do gradient-based methods, which they won't have this problem. You're always making sure that you're doing a contraction. Or their other strategy is to change that D to be very careful about it. So use reweighting. So in fact, this reweighting I mentioned in here, the emphatic weightings, is exactly to solve that problem also.
Professor, could you please share that link for me? Because I'm now working on somehow the Q-learning method the theory on that one.
Sure, I'll tell you the name if you're looking for something specific. It's called GreediGQ. But maybe more generally, you could always ping me and I'll send you some links.
Okay, thank you, Professor.
You're welcome.
Okay, let's see. Anyone else have additional questions?
I see a question. I'm just going to read it out loud.
Yeah, sure, great.
In terms of data efficiency, does greedification improve on vanilla policy gradient methods? And how does it compare to RL approaches that use the reparameterization trick and then use the pathwise derivative? Okay, in terms of data efficiency, does it improve on vanilla policy gradient methods? Okay, so I guess I don't, one of the things that I suppose we were saying is that many policy gradient methods can be seen as approximate policy iteration. So in that sense, it's not an improvement, it's just sort of a characterization. They are policy gradient algorithms, or policy gradient methods and API are not different, they're the same thing. So they sort of have the same efficiency in that sense. But I guess a more fun answer would be, could we get one of them to be more data efficient than the other? And if you think about policy gradient methods, they do want to have a QPi, or they want to have a good estimate, like an unbiased. If you want to have an unbiased gradient, you either need to use real samples of returns, or you want to try to get a good estimate of QPi. And I suppose this API view is exactly saying, well, wouldn't it be nice if we didn't have to do that? Like if we could get a much more approximate value estimate and then still characterize convergence if we're always ensuring contractions or something. So I think my hope is that it could be more data efficient in a theoretical sense. So vanilla policy gradient methods, though, like I said, are not really exactly implementing the true policy gradient. So I don't know exactly how to answer that part. Okay, and then how does it compare to RL approaches that use the reparameterization trick and use the pathwise derivative? Let me see how does it compare to that? I mean, a lot of those methods are trying to find a good way to compute this gradient efficiently. That is a good question. I have to think about how it compares to that. It's probably better for us just to do that one offline so I can actually think about it a little bit.
Yeah, because one thing that always I don't understand very well is that when you do the reparameterization trick, sometimes you get close to the deterministic gradient if you, let's say, set a very small noise, and that tends to have much better data efficiency in terms of sample. On the other hand, sometimes I use a policy gradient method and the solution doesn't really actually converge in very noisy settings. And I was wondering whether doing greedification is somewhere in between, if that interpretation is actually correct or not.
Right. I mean, that's an interesting point. For the reparameterization trick, I mean, there really are just taking the policy and parameterizing in such a way so as to make gradients more efficient to compute. But you get to choose how much stochasticity you have in your policy when you do your updates. Sort of like in these greedification strategies, we get to pick tau. If we pick tau to be really small, we want to have mostly deterministic policy. If we pick tau to be really big, then we're saying, go find for me the best stochastic policy. So maybe, I'm not sure if it's conflating the choice of how stochastic you make your policy and the reparameterization trick, which is mainly there to help us compute the gradient, I think.
That makes sense, thanks.
Welcome.
Great. Okay, I'm going to sneak in one more question of my own here. So just a general question related, I guess, to RL algorithms and how do we, in terms of classifying them and evaluating them, because just because there's we can take a theoretical perspective and look at convergence properties and other properties, or we could take a more pragmatic perspective and see how they work under different hyperparameter settings. And so there just seems to be just a very large cross product of algorithms, and both from a theoretical and practical perspective. And so what do you see as kind of being a reasonable path forward for just keeping track of and for identifying, when and where progress is being made, because there's just so many concerns to always keep in mind at the same time. And so we just generally interested in your philosophy on that. So I guess the question ultimately is theoretical and experimental considerations as to tracking progress in RL.
Right. I guess I'm probably a bit more of an empiricist than I'm a theoretician. But I guess one of the motivations for me in this work in the first place is that there's this just proliferation of policy gradient methods out there, and it's not always clear what it is that's different about it or why it's better. So I feel like one of the goals of this work was to sort of try to identify orthogonal axes or like different key underlying ideas that sort of narrows the scope down. So then instead of comparing TRPO and PPO, now you can characterize it as, both use an RKL with a particular greedification update. Then maybe you can go answer that question first and then see what nuanced implementation choices matter. But maybe at a more coarse level, we can sort of understand what are good and bad strategies. And then otherwise, I do hope for the theory to point us to good directions. So I guess I always like to see the way that my lab actually works. If I actually talk about philosophy, what we usually do is start with the exploratory phase of here's sort of cross products of different interesting things. And we do some exploratory experiments and then we see what's happening. And then we actually try to go theoretically characterize what looks like is working well and sort of try to build in that direction. I can imagine theoreticians maybe do it the other way around, where they try to hypothesize what are, the theoretical properties and what things should be promising, and then go and try to do experiments about those things. In any case, what is a good way to stay on top of all these different things that we could be doing? I think we're unfortunately a little bit in the exploratory setting because we have so much work to do to theoretically understand what is a good and a bad idea. I have no doubt that several of these things that we're trying to do are bad ideas. And we need some theory to tell us, either this is hard or it has these particular properties that makes it not do the thing we want it to do to help narrow the scope. And then hopefully we can have experiments to help us further narrow the scope.
And do you think, are we starting to overfit on some particular benchmarks, for example, just because I think sometimes without realizing there is probably some effort put into setting up the certain benchmarks so that they would be reasonably solvable by the best algorithms at that time, and then so that gets baked into the reward function and or some other aspects of the algorithm. And then future papers are kind of held to this requirement to compare underneath this this benchmark, which might be dated just because of the way it was cooked up at the time to satisfy certain criteria. Anyhow, just your thoughts on that.
I mean, I think experiments in RL are a bit of a mess right now because it's true that our benchmarks shouldn't necessarily be called benchmarks. In some sense, they should be ways for us to explore particular questions and not say my algorithm is better than this other person's algorithm. They could maybe be helpful for trying to characterize the FKL versus the RKL. I don't have a horse in that race. I don't really care who wins.
Yep. So
it is unfortunate that we try to get one line to be higher than the other line. I don't know exactly how to get around that though. That always sort of just naturally arises. But the answer is obviously yes. We have overfit to our benchmarks. The results are not particularly interesting that show one line higher than the other line. And rather we have all these interesting questions about what are even the properties of these underlying, let's say, approximate greedification strategies that we don't understand yet. And so hopefully the benchmarks are at least maybe useful for that.
Great, thank you. Yeah. Let's see, last call for questions because we are getting near the end of the time slot. Any other questions? Let's see.
One.
Oh, sorry, go ahead. Go ahead.
So one thing about these experiments with policy gradient is that it's hard to decouple the effect of optimization and exploration. Mm-hmm. So practically, do you know how to, at least in synthetic experiments, how to just decouple these things so that we know if it's an optimization problem or whether we are just doing the exploration incorrectly?
Right. I guess there is a strategy you could take, but you could really go sort of like in Q-learning style. I don't know if Q-learning was sort of designed for this dream where you could just hand it a batch of data, you didn't have to do any exploration, and you would just go find that Q star on the batch of data that you have. You could definitely, with the off-policy gradient, you could go do the same thing. You could take a big batch of data gathered however you gathered it, and then you could just go find the optimal, go find a stationary point for that batch of data, and then you would totally remove the exploration question. Now, what would you do after? Well, I guess what's the goal? In some sense, policy gradient is kind of intimately tied with exploration. We kind of want it to help us with exploration to some extent. But you're right, I totally agree. It would be a useful experiment to say, for this batch of data that I have gathered, here are the properties of using, let's say, these different algorithms that are different optimization strategies versus putting it all together and not knowing if is it because I decayed my temperature parameter too slowly, or is it because I used, you know, this optimizer versus this optimizer?
I see. And even theoretically, do you think if we want to prove convergence rates for policy gradients, we should just first stop the exploration part, and a good way to do it is try off policy first?
I guess it would make optimization results more applicable. A lot of the theory for convergence rates of these kinds of methods, some of the theory for convergence rates for these methods actually does assume, does take into account exploration. But then they do actually sometimes make certain strong assumptions about how exploration works. So if you look at some of the seminal work on conservative policy iteration, there they sort of tried to solve the exploration problem to some extent in their theory by assuming that they had a restart distribution that brought them to many different parts of the world. And so I think in some sense they were doing kind of what you're asking for here, is they wanted to characterize how good would my convergence be under this more ideal setting where I kind of got restarted in lots of different parts of the world.
I see. All right, makes sense. All right. Thank you.
You're welcome.
Do you think more of us should be using policies that can truly represent multimodal policies? Because I know in my group we're mainly just using, you know, you output the mean and maybe the variance, but typically not something that with an on policy algorithm that supports multimodal output right away. And so just wondering I'm just wondering in a practical sense, how often and how much of an improvement one could get from by truly having stochastic policies that support multimodal settings.
I don't know about that one. I was always hoping that a simple unimodal policy would be enough, but you know, Alan and Sung-Soo, who are just two students that worked on this, seem to have slightly different opinions. I know Alan, one of the students, has a strong opinion that if we had more complex policies, it would have an important impact. They tried some experiments with multimodal policies, but it was a lot messier apparently to optimize, so the conclusions were pretty unclear. So they're kind of putting it off as a next step. So maybe multimodal policies will have some benefits, but they definitely seem harder to optimize properly. I'm wondering what could a multimodal policy give you? I would imagine what it would do is it would prevent you from, say, committing too quickly. Like, you know, maybe there's two actions you think are pretty good and you're able to now say, keep some value around both. And then as time passes, maybe you start realizing the second action really isn't that good. And finally, you can kind of collapse it into unimodal. But it gives you this ability to sort of consider multiple options for longer. I don't know, maybe the same thing could be obtained by just starting with a higher temperature and then decaying that temperature more aggressively, because then you're still kind of giving yourself this chance to see more things. I don't know, Sung-Soo, if you wanted to pipe up, if you had an opinion about it, I can see you're here. You could always tell me what you think about unimodal versus multimodal.
We would love to hear.
Hello. Hi. So I think unimodal policies make you commit to a certain action sooner. So like if you have multimodal policies, I think it can definitely help with exploration in the early phase, I think.
Okay, so you guys found that yourselves.
Yeah. Like,
what about the thing about starting with a higher temperature and then decaying? What do you think that would simulate it or no?
Yeah, I think that will also help because like having a large temperature will allow a large expiration at first, and then you can slowly decay that. Yeah.
Cool. Great. Thank you. Okay, great. If there's let's see, do one last check for questions. I don't see any right now. I know. Many thanks for traveling this way virtually, and hopefully the next time we can get you to travel in person, or I know we really appreciate all the time that you spent on this, and it was a fantastic overview, by the way. So in the first part of the talk, that was super. Really
great. It was lots of fun. Thanks for inviting me. And definitely, it's a quick walk for me to get there, so I'll definitely come in person sometime.
Great. Yeah, perfect. And yeah, for those of you who wanted to follow up, they can follow up with you by email, etc. So
absolutely.
Okay, great. Thank you again so much. All right, take care. Bye-bye, everyone.